Hello class. We're going to go over in this video the things that we kind of glossed over in our organic chemistry lecture, mainly because these are just, in many cases, a review of concepts from Gen Chem 1 and 2. So one of the ones being enthalpy, represented by the symbol delta H, or sometimes Q for heat energy. This is essentially looking at how energy is being absorbed or released during a chemical reaction, and this corresponds to what is happening to a chemical bond in your reactants and products. As those electrons in a chemical bond are picking up kinetic energy through a change in temperature, increasing temperature, then that can help push them away from being bonding molecular orbital electrons to the point where they start breaking apart. Now, those bonds can break apart in two different ways. The homolytic bond cleavage, where an electron in that covalent bond goes to each of the things that were covalently bonded, and then heterolytic, where both electrons in the covalent bond go to the same end part. When it's homolytic, that's when you're going to make radicals that have an unpaired electron, and then for heterolytic bond cleavage, that's when you tend to form ions, where the thing that gained both electrons tends to gain a negative charge, and the thing that lost the shared electrons gains a positive charge. As far as bond energies, these are the energies needed to either break apart a bond or what's going to be released once that bond is broken. And interestingly, the bond between hydrogen and fluorine, that is an incredibly high energy bond that is difficult to break apart, and that's why usually we don't actually use hydrofluoric acid to fluorinate things, whereas you would use hydrochloric, hydrobromic, hydroiodic to add those types of halogens onto many types of organic chemical reactions. And then some other reactions as well, something about the fluorine-fluorine bond. It's incredibly highly destructive, and usually we don't use that as well. But for other types of reactions where you might use Cl2 to add a chlorine, you could use Br2 or I2 to add a bromine or iodine. Getting into bond energies for exothermic and endothermic reactions. An exothermic reaction is when the energy gained by bonds formed exceeds the energy needed for the bonds to be broken. In other words, energy gets released as a product, making the products more stable than reactants. For endothermic reactions, energy needed for bonds broken exceeds the stability gained by the bonds formed. Essentially, the reaction absorbs energy in order to progress. So energy is absorbed as a reactant, and products are less stable than the reactants because you're gaining more energy to go from reactants to products. Looking at our energy diagrams, the axis that is for the reaction coordinate is basically showing, are those things, are they in the more the reactant side, or are they more looking like how everything is going to be bonded in the product side? And then enthalpy, that is showing us our heat energy as our reaction is progressing. For our exothermic reactions on the left, products are lower in energy than the reactants, and energy is released as heat, which is essentially potential energy in the chemical bonds converted to kinetic energy. The change in enthalpy is a negative value from the starting position to the final position, and the temperature of the surroundings increases. Essentially, if you are holding a beaker that has an exothermic reaction, it is going to be releasing heat into the environment and it would feel warmer. Whereas endothermic reactions, as shown on the right, the starting position is actually much lower than the final position with the products. So there's actually a gain in enthalpy that is positive. Products are higher in energy. The energy is consumed, where kinetic energy from the environment, heat energy, is absorbed and then converted to potential energy, stored energy in chemical bonds. And, well, the temperature decreases because energy is being absorbed from the surroundings to get those reactants over the activation hump to form products. The sign of the positive or negative in enthalpy indicates the reaction is either exothermic if negative or endothermic if you have a positive value, and an energy diagram is used to describe two separate concepts: kinetics, which is the speed or the rate at which a reaction occurs, and thermodynamics, which is the transfer of energy as a chemical reaction occurs. Potential energy is usually shown on the y-axis, and then the reaction's progress is what's shown on the x-axis. A very common type of reaction, which is a halogenation reaction in organic chemistry, in this case a bromination reaction, taking a alkane, reacting it with bromine, whether in the presence of light or heat, adds that bromine to the most substituted carbon, and essentially the hydrogen that was removed from that carbon is now, or a hydrogen that was removed from that molecule is now part of hydrobromic acid. So in this case, the change in enthalpy is the bond dissociation energy of the bonds broken minus the bond dissociation energy of the bonds formed. For the bonds broken, there's a CH bond and a bromine-bromine bond. And for the bonds formed, we have a carbon-bromine bond and a hydrogen-bromine bond. Therefore, taking the energies of the bonds that were broken, adding them together, adding the energies of the bonds that were formed, then subtracting the difference, there's a change of negative 63 kilojoules per mole of reaction. So the change in enthalpy is negative for this reaction, making it exothermic. Entropy is another type of concept from thermodynamics, and the way that we calculate things for enthalpy is very similar to how we calculate things for entropy, or, in our words, if you're familiar with Hess's law, the same applies for entropy and other parameters in thermodynamics. Now, exothermic and endothermic reactions, they could each potentially occur spontaneously. Most reactions are actually exothermic though, which means that they release heat energy upon reacting. Both enthalpy and entropy, delta H and delta S, are needed to know for sure if a reaction is spontaneous or not, and entropy is basically a way of describing molecular disorder or the randomness or the freedom. In other words, the ability to be in many different positions. Entropy is the number of vibrational, rotational, and translational states of energy of a compound. Vibrational being moving around, rotational being rotating about a bond, and translational moving in straight line positions. Looking at the example where a gas is contained to one volume, that is a lower entropy state where there's less possibilities for those gas atoms to be oriented inside that single container, However, if the container is opened to expand the volume, then entropy increases because those gas atoms now have many more different positions that it could occupy. The total entropy change, represented delta S TOT, determines whether a process is spontaneous. A total entropy is the entropy of the system plus the entropy of the surrounding. For chemical reactions, the entropy change for both the system, which is the chemical reaction, and the surroundings, which is usually the solvent that the reaction is occurring. There is, if delta S total is positive, then that's one way of saying that the reaction is spontaneous, because that is the natural trend for entropy, total entropy, to progress. Now, the system's entropy is affected most significantly by two factors and will be positive. One, when there are more moles of product than moles of reactant. Essentially, having more moles of product means that those atoms, those elements, are able to occupy a lot more different positions than if they were just limited as one single mole. Having two different moles, A and B, instead of AB, gives more possibilities for A to orient in different positions and B to occupy different positions in space. When a cyclic compound becomes acyclic when it breaks open, that also allows for greater entropy, where in a cyclic form it's very constrained. In an acyclic form, or as a chain, it's allowed to freely move a lot more, to rotate about its bonds, to translate, to vibrate a lot easier, all increasing the entropy of the system. Recall that spontaneity of a process depends only on the total entropy. So if the entropy of the surroundings is a function of the enthalpy of the system and temperature, T, such that the surrounding enthalpy is the enthalpy change of the system of the chemical reaction divided by the temperature the reaction occurs at, multiplied by -1. So the equation for total entropy is negative delta H of the system over T plus the entropy change of the system. Multiplying both sides by temperature in Kelvin. This gets us to the equation of negative T delta S total equals delta H of the system minus T delta S of the system. Now the total entropy times temperature times -1, that's what delta G is, or Gibbs free energy. This is a valuable concept because it brings together enthalpy and entropy and temperature of our system, therefore pretty much a fuller picture of the thermodynamic perspective. Now, delta H is associated with the change in entropy of the surroundings, and the concept of T times delta S is associated with the change in entropy of the system. And free energy, this is a universal parameter that if it comes out negative, then at that temperature, that reaction is always spontaneous. Or if delta G comes out positive, then that combination of enthalpy and entropy and temperature will be a non-spontaneous reaction. Spontaneous reactions, they will naturally occur once those reactants are coming together, and a non-spontaneous reaction, it needs larger energy input to force the reaction to occur, but it will not occur naturally on its own without that energy input. good example of a spontaneous reaction, especially when it comes to organic chemistry too, is the Diels-Alder reaction, where a 1,3-diene reacts with a alkene, and essentially this allows the formation of a ring where the double bond in the diene forms to form a sigma bond between a terminal carbon to a terminal carbon of the alkene. The alkene double bond moves to form a bond between it and the diene, and then the remaining double bond of the diene just gets shifted up to form a double bond elsewhere. Since this reaction is spontaneous, delta G has to be a negative value. Now we know that T delta S will be negative because the entropy is decreasing, basically going from 2 moles of reactants to 1 mole of product. Also because you are closing or forming a ring. So it must be true that delta H is negative for delta G to be negative overall. Mainly because if delta S is negative and T, temperature in Kelvin, is always positive, then negative T delta S would be a positive parameter. In order for delta G to be negative, then delta H needs to be very negative. So the entropy of the surroundings is increasing more than the entropy of the system is increasing. If a process has a negative delta G, the process is spontaneous, and it could also be called exergonic, or it is releasing free energy. Sort of like exothermic for heat, exergonic for free energy. Notice that the energy diagram, the free energy, delta G, is plotted instead of the delta H. So looking at this, delta G is looking at the difference between the reactants and the products. Because there is a negative change from start to finish, then that is called exergonic. Endergonic is where it is actually the opposite, where the free energy has a positive value. Similar to how enthalpy would be endothermic, this would be endergonic. An endergonic reaction favors the reactant side instead of the product side because you need to gain a substantial amount of energy to overcome your activation energy hurdle, and then the products are in a higher energy state than the reactants were, which tends to not be what chemical reactions want to do. Now consider the exergonic process with a negative delta G, which means that the products are favored to form, and therefore a spontaneous reaction in the direction of forming products. An equilibrium will eventually be reached, though. A spontaneous process means there will be more products than reactants. The greater magnitude of a negative delta G, basically the more negative your delta G, the greater the equilibrium concentration of the products are. And here we're looking at the combination of reactants A and B reacting in an equilibrium reaction that eventually leads to products C and D and an overall negative change in Gibbs free energy. Now, the reason why an exergonic reaction doesn't go all the way 100% to form products is because as A and B reactants are decreasing in concentration, their collisions are decreasing as well. Therefore, you end up having enough concentration of C and D that their collisions start interacting as well. And since this is an equilibrium reaction, that would start pushing them back to forming reactants. So, as you are having less and less collisions for the reactants, its free energy is decreasing, and as you are having less and less collisions of products, their free energy is decreasing until you reach a minimum value of delta G. and that would be your equilibrium value. Now, eventually the forward and reverse reactions will equal, and when you're at equilibrium, delta G equals 0. The equilibrium constant is another value from thermodynamics, also called the thermodynamic equilibrium constant, KEQ, is used to show the degree of which a reaction is product or reactant favored. And it is simply taking the concentrations at equilibrium of all your products on top and all your reactants on bottom, but usually we ignore anything that is a solid. Additionally, we don't usually include water if it's a solid or in the liquid phase. But anything else that's in the liquid phase, anything that's in the gas phase or aqueous phase, those usually are included in our equilibrium expression. And what's not shown in this equation here is that the exponents for our equilibrium constants, they are the coefficients from our balanced chemical equation. For example, if we had 2A reacting with 1B to form 3C and 1D, then C would have the exponent 3, D would have the exponent 1, A would have the exponent 2, and B would have the exponent 1. Those exponents for the concentrations in our equilibrium expression are always the stoichiometry from our balanced reaction. We can use the equilibrium constant in our Gibbs free energy change calculation, where delta G equals the universal gas constant R times the temperature in Kelvin times the natural log or log base E of the equilibrium constant, and that product multiplied by -1. All those are thermodynamic terms, and they only describe the relative stability of the products and reactants, but they do not tell you how quickly the reaction actually occurs. For example, perhaps a spontaneous reaction might take milliseconds to occur. Maybe it could take 100 years for that reaction to actually occur. Spontaneous just means that it can occur naturally on its own, where non-spontaneous means it does not occur naturally on its own without substantial energy input. Looking at equilibria and numerical examples, well, let's see. A -17 delta G could be from a 10 to the third KEQ. Let's see. That would be percent of products at equilibrium, almost 100%. And then as that value in delta G is becoming less and less negative or more positive, then the percent products is decreasing and you have more reactants at equilibrium. Now again, the negative sign in front of delta G means that the process is product favored or spontaneous in the direction. This does not tell anything about the rate or the kinetics of the process. In other words, delta G says nothing about how fast a reaction will occur. Some spontaneous reactions are very fast, like what happens in explosions. Other spontaneous reactions are incredibly slow, like the natural progression of carbon in diamond to turn to carbon in graphite. That takes millions and millions and millions of years. So usually your family jewels for diamonds are pretty much stable for all of your family's history, even though it is a spontaneous reaction to move toward graphite. The reaction rate of a function, or the kinetics, is dependent on or is a function of the number of molecular collisions that will occur in a given period of time, and it's affected by 5 factors. The concentration of reactants. As you increase concentration, there's more chances for A and B and C reactants to all collide and then start working toward products. The activation energy, as that activation energy decreases, then it becomes easier or quicker for reactants to then collide and form products, to have enough energy to collide and form products. As the temperature increases, then that's increasing the amount of kinetic energy, thus increasing the probability of a collision. The geometry and sterics, basically for the parts of molecules and compounds that need to interact, are those spots very easy to meet, or are there a lot of side groups that make it more difficult for the right parts to match? And then the presence of a catalyst, that just increases the rate that a chemical reaction can occur. It does not affect the thermodynamics whatsoever, but it does affect the kinetics by lowering the activation energy needed to bring reactants together. Now, in this case, for kinetics, we have a rate law, which a rate in units of molarity per time is some rate constant multiplied by the concentrations, the starting concentrations of all your reactants. Now, each reactant is going to be raised to a coefficient, and that coefficient is your rate order of that reactant. But those exponents for kinetics have nothing to do with the balanced stoichiometry and are actually different values that are calculated in a different way. So the rate depends on a rate constant and the concentration of your reactants. The degree at which a change in reactant occurs will affect the rate in a way known as the rate order. If all your reactant exponents add up to 1, then your reaction is first order. Essentially, as you change the concentration of A by, if A is doubled in concentration, then the rate is equally doubled as well. If all your reactant rate order exponents add up to 2, then your reaction is overall second order. However, if individually your reactant A is, if A is doubled, the rate is doubled. But in the case, if all your exponents add up to 3, then the reaction is third order. Now, in the first two cases, the reaction was first order with respect to A because A's concentration was raised to the first power, so its effect on the rate is the same. Double its concentration, the rate is doubled. Now, in the third order case, the concentration of A is not raised to 1, but is raised to 2. That means that that reaction is second order with respect to reactant A, is overall third order because the exponent of B is 1, and 2 plus 1 equals 3. But if you keep B's concentration the same for the starting concentration in multiple trials, but you are changing the concentration of A in each of those trials, then if A's concentration is doubled, then that quadruples the rate of the reaction. In general, your rate law looks like this. The word rate equaling some rate constant K, and then all of your reactants in brackets, that means concentration of that reactant, raised to different exponents, x, y, so 1, 2, 3, 0, 1/2, usually whole numbers. Now, if we're looking at the activation energy, this is the energy barrier between reactants and products. Basically, how much energy is needed at the start of your reaction to get it to a point where it will then have enough energy to fall all the way down to products. It's the minimum amount of energy required for molecular collisions to have enough energy to progress two products. Oy. The activation energy in this case, the energy barrier between reactants and products, as EA, or the activation energy, increases, the number of molecular molecules possessing enough energy to react decrease. Essentially, the harder it is to reach the top of the hump, the less of your molecules are able to overcome that activation energy barrier hump. Now, the lower the activation energy, the faster the rate, because it's a lot easier to overcome, and there are going to be more reactants that will collide with enough energy to overcome that smaller hump than when there is a larger hump. And that activation energy barrier is rate determining. Basically, the bigger it is, the slower your rate, the smaller it is, the faster your rate will be. Now, factors that affect rate, constant, and temperature. Raising the temperature will result in a faster reaction because you are adding more kinetic energy to your system, increasing the collisions and increasing the amount of energy those collisions have. At higher T, the molecules have more kinetic energy, and at higher T, more molecules will have enough energy to react and produce a reaction. Steric considerations, basically steric hindrance, that is a popular term in organic chemistry. Steric hindrance and the geometry of a compound affect the rate of a reaction. When molecules collide, they must have the correct orientation for bonds to be made and broken. If the reactive conformation of a compound is high energy, it will spend less time in that conformation, and so the probability of collisions resulting in a reaction is lower. When a catalyst is added, it simply speeds up the rate of a reaction, and it is not consumed. Basically, if it is modified at the start of a reaction, then it is reformed by the end of your reaction, or it simply is not actually modified in any way, but just brings the reactants closer together with enough energy to react in the right position, and then allows the reaction to occur quicker. Now, catalysts provide an alternate and faster pathway for a reaction. Catalysts lower the activation energy. Now, if your reaction is an equilibrium reaction, then your catalyst works both ways. It helps the reactants form products, and products go back to reactants. It decreases the activation energy, and it can help you get to an equilibrium a lot quicker as well. However, if your reaction is just one directional, then it helps the reaction move in that direction by decreasing the activation energy every time. In this case, we see where the potential energy, or the amount of energy needed to be overcome for our activation energy bump, is much lower when a catalyst is present than when a catalyst is not present. But again, this decreases the activation energy both for the forward direction and the backwards direction. So, kinetics and thermodynamics, they are very different. They are completely different concepts, and the cool thing is we can look at both of them usually in our energy diagrams. In this case, the rate of a reaction, the kinetics, can be modified by the activation energy bump. And then the thermodynamics, though, does not depend at all on the kinetics, because no matter what, your reactants start at the same position and your products end at the same position. And that will give you the same delta G, or free energy change. In the case of looking at when C and D is favored, if A and B could potentially become E and F, or could become C and D, consider this diagram here, which describes two possible pathways for reactants A and B. The formation of product C and D has a lower activation energy, and they are at a lower energy state than E and F. So the products C and D form faster than E and F, and C, D form more stable, lower energy substances than E and F. Therefore, the formation of C and D is both kinetically favored because it's faster, and thermodynamically favored because it has a lower activation energy and it has a lower energy at the end of your reaction than from the start of your reaction. Now, there can be cases where kinetics and thermodynamics are actually competing. Looking at the formation of E and F versus C and D, according to the following energy diagram, the formation of E and F has a lower activation energy and will occur quicker than the formation of C and D. However, the products C and D are lower in energy and therefore are more stable than forming E and F. The formation of E and F will therefore be kinetically favored by speed and activation energy, but the formation of C and D is thermodynamically favored still, because those products of C and D are lower in energy than E and F, making them more stable. Two different concepts that we can see in our diagrams can be transition states and intermediates. Transition states are when you have that maxima or a high point in your energy diagram where it goes from positive to negative slope, and then intermediates are where you have minima in your diagram where they go from negative to positive slope. Transition states, they cannot be observed because the second that you have enough energy to reach that point, there's already enough energy to move forward into the next part of our diagram. However, intermediates, they actually can be observed physically, and because those molecules or those substances will be in the intermediate position for a little bit of time until they absorb enough energy to then go to the next part of the diagram. So transition states represented in brackets around the theoretical look of the molecule. The brackets in this case were not representing an ion. That double dagger symbol to the top right of it is just to mean this is a transition state and not a physical thing that we can actually observe. The dashed bonds in this case, they're different from the dash bond of our 3D representation, like for dashes and wedges. In this case, our dashed bond is showing a bond that was already present but is starting to break apart. So in this case, that bromine carbon bond that was already present is starting to stretch. The carbon and bromine are starting to separate further and further apart, while that chlorine is starting to get closer and closer to the carbon, and a chemical bond is starting to form between the two. So overall, this carbon is still not bonded 5 times because a pentavalent bonded carbon pretty much breaks all of organic chemistry and should never ever be drawn, ever. Now, transition states, they're fleeting. They cannot be observed because, again, the exact moment that there's enough energy to reach that point, it's already moved past that point to then go toward a lower energy state. On the energy diagram, the transition states are always energy maxima and represent the transition as bonds are made and or broken. An intermediate is an intermediate species formed during the course of reaction. They are energy minima on the diagram. The intermediates are observable They are an actual chemical species that exists for a period of time before gaining enough energy to move further in the reaction. So, usually when you have your intermediates, you're seeing carbocations form. Therefore, if you have intermediates, you have a multi-step reaction, and if you just have a transition state, that could be situations where you have a concerted reaction that is a one-step reaction. So, transition states, you might have concerted reactions, one-step reactions. Intermediates, you may have multi-step reactions, like two-step reactions that are not concerted. And usually you have your carbocation that's formed when there is an intermediate. In this case, you have your bromine that's bonded to your alkane. It breaks off, forms an ion, and you're left with a carbocation intermediate, and then that intermediate can then react with the chlorine anion to form your alkyl chloride, and leaving bromine as an ion. To one last concept, the Hammond postulate. 2 points of an energy diagram that are close in energy should be similar in structure. Based on this assumption, we can generalize the structure of a transition state depending on whether the reaction is exothermic or endothermic. In the case of an exothermic reaction, the transition state is going to more resemble the reactants, the starting material, whereas for an endothermic reaction, the transition state is going to resemble more the products. The reason is because for exothermic reactions, you are overall releasing energy by the end of your reaction. So reactants are in a higher energy state than products, and you need to gain energy no matter what to get to a transition state. So that gain in energy is still closer to the position in energy that the reactants were at, and is very different than where the products are at. For endothermic reactions, you are overall absorbing energy, and there is more energy in the product state than in the reactant state. So every time we need to absorb energy to get to the transition state. Because the transition state is absorbing energy, its energy position is going to be closer to the products in energy. Therefore, it will look more like the products. So going back to this, in this case, we see our transition state where our chlorine and bromine, they are relatively close together. The bromine is still relatively close to the carbon, similar to how it is in the reactant state. And then as we are progressing along, that chlorine-carbon bond that's forming gets more closer, and then that bond that's breaking apart between carbon and bromine is breaking fully apart. While there's still partial bonds, that's where you're going to see partial charges. And then once they fully break apart, that's when you have a full charge on the bromine. In any case, that concludes our review of the thermodynamics and kinetics that was covered in general chemistry that we glossed over during our lecture in our class for organic chemistry. Now, just for anyone who's not watching this for the class, if you would like to subscribe to the channel, you can. I like saying that because that usually makes the subscribe button glow like a rainbow. Or you can like the video or comment it, and if you don't, that's okay, because that's just more or less a fun thing to do. In any case, for those of you who are in my class, glad to have you all, and glad to have you all for the remainder of the semester, and wishing you all the best, and as always, peace.